Good morning, everyone. I'm from the farm. Welcome to the course Food Waste Management. This is the practical module of the study unit Circular Economy Principle and Sustainable Practice in Food System. It belongs to the second module, Environmental Impact Assessment and Management. The practical activity focused on applying environmental sustainability assessment to food product design and production method, building on theoretical concepts introduced earlier in the unit. You will learn how to use the simplified life cycle assessment approach to examine how different design and production choices affect environmental performance across the food product life cycle. This activity will guide you in identifying key environmental impacts, comparing alternative scenarios, and recognizing critical hotspots related to resource use, emission, and waste. The activity will support the learning outcome by developing analytical skills, system thinking, and ability to evaluate food product and production method using established environmental sustainability criteria. By the end of this activity, you will be able to assess product design and production method using established environmental sustainability criteria. In this exercise, we will analyze a simplified life cycle assessment of tomato sauce product. The scenario is about a food processing company that want to review two tomato sauce product lines that have same processing procedure, but they are different in agricultural sourcing, packaging type, and shelf life characteristic. A simplified life cycle assessment is performed to compare the environmental performance of two products and support strategic decisions related to product design, packaging selection, and waste reduction. The analysis focuses on key sustainability dimensions, including ingredient-related impact, packaging circularity, food waste prevention, and environmental efficiency per unit of nutrients delivered. The assessment is carried out per unit of product actually consumed by consumer. The functional unit for calculation is 400 grams of starch consumed, which is also the net weight of each product. In this table, you can see all the product information. As I mentioned, the net weight for both products is 400 grams. The main ingredient, which is tomato, for product A comes from conventional agriculture, while for product B, the tomato is produced from organic agriculture. The packaging of product A are glass jar and metal lid, while product B use a plastic recyclable pouch. You can also see the packaging recycle rate. In case of product A, the rate is much higher than product B. And also the shelf life of product A is twofold compared to the product B. After the opening, the product A can last 5 days at the 4 degrees, so in the fridge, while product B only lasts 3 days at the same condition. In the second table, you can see the simplified dataset for each product. The impact per 1 kilogram of starch produced includes the impact from ingredient cultivation, processing, and distribution. This term distribution refers only to the distribution of the product, not the packaging. The distribution impact related to packaging weight are included in packaging impact that you can see in the row below. The impact also includes the consumer refrigeration after opening, and the waste after opening is the food that is waste when the product is at the consumption stage. You can also see the nutrition value. For both product, per 100 gram of consumed starch, we have 1.5 gram of protein and 40 kilocalories of energy. The first task is about ingredient choice and environmental impacts. You have to answer which option has lower ingredient cultivation, which is measured in CO2 equivalents per kilogram produced. You have to mention two additional environmental considerations that make conventional and organic tomato production different. The second task is about packaging sustainability assessment. Which packaging has lower packaging production? Explain briefly why packaging impact can be different even if the net product is the same. And then you have to give one comment on recyclability and real recycling rate. In the third start, you have to calculate total carbon footprints of each product. And after that, we have the fourth start, which is for a unit of product, you have to calculate the kilogram of CO2 equivalent per gram of protein, kilogram of CO2 equivalent per 100 kilocalories, and you have to answer is per kilogram protein a meaningful metric for tomato sauce? Why and why not? The last task is about interpretation and improvement. Which option is better overall in this simplified life cycle assessment? Identify the hotspot of impact for each option and propose three improvements for ingredient, packaging, or food waste reduction, which is about shelf life and consumer use. Since the third and the fourth task require some simple calculation, you will need a portable calculator or Microsoft Excel. I would like to suggest a procedure of calculation for the third and the fourth task. In the third task, you will start by calculating how much starch must be produced. In this case, the functional unit for calculation is 400 grams of tomato starch actually consumed. However, not all the starch produced is eaten because there's a fraction of waste after opening at the consumption stage. So, to make sure that 400 grams is actually consumed, the company must produce an amount of starch that is actually higher than 400 grams. For this reason, we have to calculate the amount of produced starch before calculating environmental impacts. The real amount of starch that must be produced is equal to functional unit divided by 1 minus waste rate. In the next step, you have to calculate the product impact per functional unit, which is equal to product per kilogram multiplied by the real produced real amount of produced starch in kilogram, which equal to the sum of ingredients, processing and distribution impact per kilogram multiplied by the real amount of produced starch in kilogram. So the total carbon footprint per functional unit is equal to the sum of the return you obtain in the second step plus packaging and refrigeration. For the task for A and for B, you must start by calculating the total amount of nutrients or energy delivered in a functional unit, and then you calculate the carbon footprints per gram of protein or kilocal equal to the total carbon footprints per functional unit divided by total amount of nutrients or energy delivered in a functional unit. Now we are going to start the first task, which is about ingredient choice and environmental impact. The task 1A is a comparison of impact during cultivation stage. From the data set, we have the impact from ingredient cultivation of product A is equal to 1.10 kilogram CO2 equivalents per kilogram of source produce, while in case of product B, the impact is only 0.95 kilogram CO2 equivalents per kilogram of source produce. So the product B has lower climate impact at the ingredient production stage. The lower value for organic tomato reflects the reduced reliance on energy-intensive synthetic fertilizer and pesticides. From this data, we can see that the organic agriculture has the benefits that outweighs the potential yield reduction. The carbon footprint is a key indicator, but we also have to consider the other factors like water use and water pollution. In case of product A, because the tomato used in product A come from traditional agriculture, it can involve the use of synthetic fertilizer that can be a pollutant. So, overall, organic production is often expected to perform better in terms of water quality protection. Although the local condition and management practice still remain critical. Soil quality and biodiversity. The product A relies on traditional agriculture, so they may use the practice like monoculture that is not very eco-friendly, while the product B use organic tomato that maybe they use more eco-friendly practice like regenerative agriculture and reduce of synthetic input. So organic system contributes to the long-term resilience of agriculture system and are central to sustainability beyond short-term productivity. About the use of agricultural input, the product A typically use synthetic fertilizer as mentioned and chemical pesticides, while product B limits synthetic input and instead rely on organic fertilizer and biological pest control. So, for general consideration, ingredient production is frequently one of the largest contributors to the overall environmental footprint of food product because it involves the direct use of land, water, and nutrients. It can cause the emission that come from fertilizer production and soil processes, land use change, and biodiversity loss in some cases. So even when the processing and packaging are optimized, the unsustainable ingredient sourcing can dominate total impact. For this reason, the ingredient choice is a critical leverage point in sustainable food product design. The second task is about packaging sustainability assessment. About the packaging production impact, from the data provided, we can see that the packaging in case of product A is equal to 0.30 kilogram CO2 equivalent per package, while in case of product B is much lower, only 0.12 kilogram of CO2 equivalent per package. So we see clearly that option B had a significant lower packaging related climate impact. The glass production require higher temperature and a large amount of energy. And also the glass packaging is more heavier and it increase the energy used during manufacturing and handling and transportation. On the other hand, flexible pouch use much less material mass and they require less energy during the production. So even though both products contain the same net amount of starch, the packaging impact are different due to the material type because the glass is more energy intensive to produce than plastic-based flexible material. About the material quantity, the glass jar requires more material mass to provide a rigid structural strength and processing requirement for the production of glass, in particular, the melting and forming glass requires sustained high temperature. Well, so flexible packaging film are produced at lower energy intensity. On the other hand, considering the recyclability and recycling rate, glass packaging is widely recyclable and can be recycled multiple times without significant loss of quality. In many regions with efficient collection system, the real recycling rate of glass are often relatively high. While in case of flexible pouch, in theory they are recyclable, but often they face challenges in sorting and recycling due to multi-layer structure and limited infrastructure. Usually, the flexible pouches are not monomaterial, but they use multiple layers of different kind of plastic, so it can complicate the recycling. For this reason, the recycling rate may be much lower than the theoretical recyclability suggests. From this analysis, we can see the importance of distinguishing between design intent and real-world performance in sustainability assessment. The packaging play two roles in food system. It contributes to environmental impact to material production and disposal. But on the other hand, it has a purpose of protecting the food product, extending the shelf life, and reduce food waste. In some cases, a packaging solution with higher material impact, like glass or metal, may still be environmentally justified if it significantly reduces food waste. In contrast, lightweight packaging with lower material impact may lead to higher overall environmental burden if it results in increased product spoilage. So, the packaging sustainability must be evaluated together with shelf life and food waste consideration, not only the packaging itself. For the third task, we have to calculate the total carbon footprint. So in this task, we will have to carry out some calculation. Firstly, we calculate the amount of starch that need to be produced. The product A generates 3% of waste, while the product B generates 5% of waste. So There are only actually 97% of product A is actually consumed, while in case of product B, there are only 95%. Since some waste is weighted after opening, more than 400 grams must be produced to ensure that 400 grams is actually eaten. By applying the formula, we obtain that the real amount of source A that needs to be produced is equal to 0.412 kilogram, while in case of product B is roughly 0.421 kilogram, which is slightly higher because product B generates more food waste. Next, we have to calculate the product impact per functional unit. Applying the formula, we obtain that the product impact per functional unit of product A is equal to 0.618 kilogram CO2 equivalent, and in case of product B is 0.568 kilogram of CO2 equivalents. Now, to calculate the total carbon footprints per functional unit, we only have to sum up the reason we obtain in the second step with the impact that comes from the packaging and refrigeration during consumption. In case product A, the total carbon footprint is 0.93, and in case of product B is roughly 0.70. The impact from packaging and refrigeration are not adjusted according to produced amount of storage because it is simplified life cycle assessment. The consumer buy 1 unit of packaging of product. So even if a small share of the storage is weighted, we calculate the impact based on the total amount of storage produced and 1 unit of packaging. From the reason, we see that the product B has a lower climate impact per functional unit, and even though product B has slightly higher waste rate of storage, it still have a lower impact because the cultivation impact is lower and also much lower packaging impact. The fourth task is about nutrition and environment optimization. Firstly, we have to calculate the carbon footprints per gram of protein. For both products, the protein content is 1.5 gram per 100 gram of product. So the protein content in a functional unit, which is 400 gram of product, is equal to 6 gram of protein per functional unit. To calculate the carbon footprints per gram of protein, we have to divide the total carbon footprint per total protein content in a functional unit. For product A is equal to 0.155 kilogram CO2 equivalents per gram of protein. While in case of product B is slightly lower, which is 0.116 kilogram CO2 equivalents per gram of protein. So with this indicator, we see that the product B is better. Now we are going to calculate the carbon footprints per 100 kilogram. For both products, there are 40 kilogram per 100 of gram products. So with a similar calculation, we obtain the carbon footprints per 100 kilogram for product A is equal to 0.581, while in case product B is equal to 0.435. So also in this case, in this indicator, the product B is better. Is per gram protein a meaningful indicator here? The carbon footprint per gram protein is only partially meaningful because the tomato starch is not rich in protein. So normalizing the impact by proteins can be misleading. It can make tomato starch look inefficient simply because it contains little protein, even though its purpose is favor the vegetable intake rather than protein supply. For tomato starch, a more appropriate functional comparison often per serving for example 100-gram consumed or per meal functions. For example, the starch portion used in a pasta dish. So the nutrition environmental metrics are useful, but only if they match the product nutritional role. The last task is interpretation and improvement. Firstly, we consider the overall evaluation based on the results of simplified life cycle assessment. The total footprints, carbon footprints of product A is 0.93 kilogram CO2 equivalents, while in case of product B is roughly 0.70 kilogram CO2 equivalents. So, considering the overall carbon footprint, the option B is preferable for climate impact per 400-gram consumed. Packaging and ingredient stage improvement in case of option B outweighs the slightly higher waste rate. Now we identify the hotspot of impact for each product. In case of product A, packaging is a major hotspot because the glass jar impact is 0.30, which is roughly 32% of the total impact of product A. And also ingredients are significant, can contribute to the environmental impact because the cultivation in product A is traditional agriculture, so it leads to a higher environmental impact. So for product A, the design priority is reducing packaging burden with a lighter weight, recycle content or reuse, and improving agricultural performance. In case of product B, the ingredients remain the largest contributor. Packaging impact is lower than product A, but the end of life could be problematic because it's less circular. And food waste in the waste rate in case of product B is also higher. So for the product B, the design priority is keeping ingredient impact low by using the organic ingredients and improve supply practice, improve pouch recyclability in practice, and reducing waste after opening to shelf life design. For the improvement strategy, firstly, we're considering the ingredient choice for both options. We can switch to regional or seasonal sourcing where feasible. It can reduce the transport distance, cold storage need, and support supply chain transparency. And also, we can adopt regenerative or integrated practice like better nutrients management, compost, and cover crop. In this way, we can reduce input-related emission, improve soil health, and lower pollution risk. Considering the packaging sustainability for product A, we use mainly glass. We can reduce glass mass and increase the recycled glass content. In this way, we reduce the footprint of packaging while keeping strong recyclability benefit. Also, we can consider the refill reuse practice. For example, the deposit return of packaging in local market. The reuse can outperform the single use if returns cycle are sufficient. And for product B, which use the plastic pouch, we can redesign to a mono-material pouch that is compatible with local recycling. It improves the real recycle outcome and reduce the end of life burden. We can also add the clear how to recycle labeling. So in this way, we can increase the correct sorting and improve the real circularity. For the shelf life and food rate reduction, we can improve post-opening usability with resealable closure, smaller pack size, so the consumer won't waste the product after the opening. A clearer storage guidance and a better barrier material that extend open shelf life by 1 or 2 days more. Even more reduction in household waste reduce upstream impact because less product must be produced to deliver the same consumed amount. So generally, the product A has better potential reward recyclability because it's your glass as packaging, but it can lead to higher production emission. While product B has lower packaging emission, but may have lower real recycling rate and slightly higher waste. Sustainable design require balancing trade-off across the life cycle, not only focused on one specific stage. Thank you for your participation. I hope you find this lesson useful and now you can apply the life cycle assessment also in other scenarios. Goodbye and have a nice day.